Welcome to the session. And for speakers, Moni Naor will tell us about permutation.
Thank you. Thank you for inviting me. It's really a great honor to speak at the conference in honor of Russell. So I think you heard a lot about Russell and his influence. I really have very little to add because it's essentially all of the above. What Paul was talking about, how the Russell way of thinking and how it influences you. And really to this day, whenever I think of a problem, if I want to sort of make sure I'm doing the right thing, I have in mind a little thing, what would Russell say? So even if it's really outside his area of interest, I still have in mind what would Russell say. So anyway, so I chose today to talk about something, not something directly related to things that Russell did. I'll mention him very briefly in passing at some point, of course. I mean, you can't avoid it altogether, but it's not directly related to anything Russell did or stuff that we did together. So on the click on? Click on this window. If you were okay, good. Good. So the stuff I'll tell you about is joint work with my students Boaz Menuchin and Roy Magen. So those of you who heard me last week, it's also, you can view it as something related to what I was talking about, the communication complexity, but it's the stuff I didn't get to talk about. And the general theme is what effect do adaptive adversaries have on the complexity? So you choose a setting where randomness helps. You show a good algorithm against static adversary and show what happens against an adaptive one, and then discuss whether crypto can help. This is, of course, where Russell comes in. And then the question is whether you can show that these tools are essential, and then you repeat it on another problem. So that's what we'll do today. So I'm going to talk about hard-to-guess permutations based on a couple of recent work, one with Boaz Menuchin, the one on mirror games with Roy Magen, and then I'll mention some work in progress on low memory generation of hard-to-guess permutation. So here's the problem, guess the card. So it's a very boring game. You have two players, a dealer and a guesser. The dealer holds a deck of n cards, each distinct. And in each turn, the dealer draws a card. The guesser guesses the card. The dealer has the card. You cannot change it. The card is fixed when the guess is made. And the card is revealed and discarded. If the guess is correct, the guesser gets a point. Very simple game. And the question is how many cards the question is how many cards do we expect to guess correct? That's a very simple game, a very simple question, especially if you have perfect memory. If you have a perfect memory, then what can you do? You'll guess one of the cards that you, and you assume that the deck is, let's say, shuffled at random. Then you'll have the nth harmonic number because at first you'll have 1 over n, probability 1 over n, then 1 over n minus 1, etc. This is a question in Kleinberg and Tardish's book. On the other hand, if you have absolutely no memory and you cannot recall, nothing happens as you go along. You always guess one of the cards. You're going to be correct with probability 1 over n for n rounds. Expectation is 1. With perfect memory, it's ln n. With no memory, it's. And the question we'll be asking is, what can you do when you have m bits of memory somewhere in between? We have m bits of memory, and what can you do? And as we'll see, it really depends on the dealer. What do you assume about the dealer? So we'll think of three flavors of dealer. The random shuffle dealer shuffles the deck properly and draws the cards one by one. That's random permutation dealer. We'll have the static dealer that prearranges the deck in some specific bad order. And the adaptive dealer that draws sees all the guesses that the guessers made and decides on the next card based on those guesses, but of course not on the current guess. That would not be very fair. So that's the adaptive dealer. And these are three types of dealers that we'll have in mind, and we'll see what you can do. So just to make sure we understand the model, it's not as complex as Manuel's model, but we have the memory of size n. We have, that's the guesser. What is the guesser look like? And there's a function mapping the current state plus card to a new state. There's two types of randomness: long-lasting randomness, and this should be counted. Should count it as charge it for your memory, but we'll sort of keep it in a separate chart. Frequent long memory user or something like that. And then on the fly, random bits that we don't count, these bits, you know. So this is the memory side M, the long lasting bit, the current card, and all this is mapped to the state transmission function, plus the on the fly randomness to a new state. You see that the state has changed. Rather, the long-lasting randomness is not changed, and of course, the new guess. Guess the key. This is. Pardon? The long-lasting I've chosen. Let's say. You don't change. I mean, if you want to convert this long-lasting vision, other than for you deeply certain. Okay, and actually, the way it will work in the possibility results will count explicitly all the random bits, and for the impossibility results, they will hold even with an unlimited number of long-lasting. The best of both worlds. Okay. So, well, we'll see what you can do against a random dealer. I think about the static dealer. If mention the lower bounds against a random adversary, you see what you can do about adaptive adversary. Then talk about background and related work and some open problems. And related work is actually stuff done in this universe. So here are some basic guessing techniques. One is simply think of the first M cards. Let's say the cards are numbered 1 through N. So you concentrate on the cards numbered 1 through M. You have a bitmap for them. And you follow them exactly as before, ignoring anything outside. This would give you ln N. That's good. And we do better than this. Well, you can actually remember the last cards also. The last cards that are appearing. You don't explicitly remember them, but using coding, you can figure out if you use something slightly, you need slightly more bits for that, but you can also figure out the last, let's say, M over log N card. Using M bits, you can figure out the last M over log N cards. How? Well, if you think of it by using, if you track their sum mod N, you can figure out the last card. Right, that takes you log N bits, and by the last card, you can know it for sure because you keep the sum mod n, and you see which one. And you can generalize this using coding to remembering the last n card. Okay. So using these two things together, are they compatible? Well, when m is roughly square root of up to square root of m, they work well together, right? Because we expect these guys to finish more or less, be done with these guys by, if we have m which is less than square root of n, we expect the last yellow guy against a random shuffle to end roughly around square root of m, so we'll get all the benefits here. And from that point on, we'll get the benefit of the green guy. So using square root of m, square root of n memory, m equals square root of n, we can get roughly roughly ln n. Okay, so we can definitely do better than this. Is good. Is this the best? So I was thinking all along, what would Russell say at this point? Okay. In fact, we can do better. There is a randomness method using m bits of memory that obtains log. You can get log n, a minimum of log n, and square root of n. Of course, you can never go beyond ln m. You can never be better than. Okay. So really, if you want to get 1 minus alpha ln n correct guesses, you need something like log squared n times log 1 over alpha. With log cubed bits, you're pretty close to what you get with perfect memory. Log cubed bits give you very close to perfect memory. And what is the idea? The idea is rather simple. And you can probably work it out from known results on in streaming and sketching, if you think about it. So for a collection of subsets of size, the general idea is that you will have a collection of subsets of the full thing, and you follow these subsets. We're talking about the random shuffling now. You'll follow the cards that appear in those subsets. For each one, you use the two accumulators, the sum of the values of the cards seen so far and the number of cards seen so far. So that's 2 log s. So that's order log n memory. And what you want, if at any point in time, if there is a subset where all cards but one have appeared, then you can detect it because you're counting how many appeared you're following how many appeared in each subset. And you can detect it, you can figure out the missing card. And this card is a reasonable guess. By reasonable guess, we mean that there is a chance, an equal chance that it will appear. So you have a reasonable guess. One question is what happens if there are 2 such subsets? There are 2 reasonable guesses, which one you pick. So here is a hint, for instance, the way we think of a simple construction is we'll make sure that there's only, any point in time, there's only one reason, because there will be actually shrinking. So, so this is the idea. This is the idea, and of course we take all powers of 2. These subsets will be powers of 2, and we'll see that this works rather well. Okay, because at any point in time you have, let's say, even with one such collection, even with this simple construction, you have a constant chance that you have one set missing, or it's better perhaps to think about it this way. You want to chart, each subset gives you a guess, a reasonable guess at some point. The problem is that it could also be the guess that the larger subset gives you. So who are we going to credit? We're going to credit the largest subset for each reasonable guess that for each reasonable guess, we're going to give credit to the largest subsets that contain it. So the analysis would be, what are the chances that the last card here is not the last card here? That's just the ratio between these two sets. You get, let's say, a constant. This is how you get to the log n. And in fact, this is the best you can do. You cannot do better. So no guesser with m bits of memory can make more than square root of m correct guesses against a random shuffle dealer. And the idea is to use the guesser in order to encode some ordered subset. So the guesser makes some correct guesses. So what we're going to do, we're going to use whatever you want to call it, the compression method, encoding, Kolmogorov complexity, Solomonov complexity. We are going to encode ordered sets, and we'll show that a good guesser, a guesser that makes more than it should, more than square root of incorrect guesses, can encode, we can use it in order to get a succinct encoding of an ordered set. Using, what do we need to do? We need to specify when the correct guesses occurred. And of course, we need to specify the memory. So we'll run the guesser for like a number of rounds up to a certain point, look at what it contains, and then it's supposed to contain some ordered subset. Then it's supposed to guess many elements of some ordered subset. So we need to encode the memory at the breakpoint, and we need to say when the correct guesses occurred, and that will give us a lot of information about something. That's the idea of the lower bound. Okay, so this part, and the thing is about compression method, that long-lasting, the fact that you have a lot of long-lasting random don't help you. You cannot compress using a lot of random. Still difficult. Okay, so now the interesting question is what happens. So about what happens. So this is optimal. So it means you cannot go below. If you want to get to, let's say, the log n regime, you cannot go below log squared. But it's not clear. Like, let's say if you really want to get to ln n, I said you need log cubed. That's not clear whether this simplification from some constant times log n to ln n in terms of the expected number of guesses, whether that requires really going from log squared to log cubed. That's actually an open. The other thing is that what happens, so this really, if we look at this picture in the story I told you, this really assumes that you have the adversary is random. You know, the shuffle was random. If you know the subset, then of course you'll pick the guy that appears right here and you put it at the end. This whole system would. So the idea of working against a static adversary is not too difficult. You apply essentially a pairwise independent permutation several times on this sort of system, and you will get amplification. The analysis is going to be a little bit different, but you get essentially the same type of thing. So this handles the random case, where the permutation is random, and the static adversarial. The adversary doesn't see your guesses. That doesn't. The permutation is independent of the guesses. But now we're moving to the case, the adversarial case, when the dealer can choose the cards adapted, sees everything that was made so far, all the guesses that was made so far, does not see inside. We go back here. The dealer does not see what's inside here. Not see the red part here. Don't let him look inside. We'll talk about that later. About the dealer does not look inside here, sees the guesses that were made, and chooses which card to put next based on the previous guess. So at step I, the dealer bases its next card on the first I minus one. Okay, and so the dealer can choose the sequence based on the guesses made so far. Does not see the internal state of the guesser. We call, in case he does see, we call it an open book algorithm, an open book guesser. Sometimes there was a recent paper that called such things white box, but I prefer to call other things white box when you see the program. And you can ask, does the dealer even know the algorithm of the guesser? Perhaps you don't know the algorithm of the guesser. And does the dealer even know the size of the memory? Maybe you don't even know the size of the memory. You assume he has, the guesser has some limited memory, but perhaps you don't know. The dealer doesn't know what it is. And we'll actually be dealing with all those cases. Okay, so first, if you think about it, the two basic techniques that I showed you first with the yellow and the green stuff, they still work. Right? I mean, if you concentrate on the first, on the cards numbered 1 through M, and completely ignore the rest, and each time pick a random card that is, now it's important to pick a random card that has not appeared so far, then it works perfectly well. You'll get lan M using this technique, right? You remember the yellow guys, ignore everything else. Each time you pick a random value, your expectation is still lan M. If you think of the other technique, the green technique, where you encode the cards that you haven't seen so far, and then of course pick a random one each time, so the dealer wouldn't be able to diagonalize against you, then this works also well. So you get another type. It's a little bit less than lan M, but they don't work together. Because the natural thing for the dealer to do is to take the yellow guide and put them towards the end. So you can destroy the yellow guide. So the yellow and the green would work together, and that's completely useless. So we have lan M is the base, is something that works, but we don't have two lan M, for instance, if we have square root, even if we have lots of memory. Even if M is relatively large. Okay, so these two schemes now are not compatible. And now, in fact, it turns out that there isn't much you can do. So you may as well give up if the dealer isn't happy. So for every M, there exists an adaptive dealer DM against which any guesser G with M bits of memory makes at most lan M plus order log n correct guesses and expectation. So you cannot, for instance, even if you have square root of n bits of memory, you're not going to do better than lan M. Even if you have close, let's say M, even if you have, let's say, n to the epsilon. You're still in the lan M regime. You're not going to go. And you don't even need to know what is the algorithm of the guess. Completely oblivious to the algorithm. And there is even a dealer that doesn't need to know the size of it. There exists a universal dealer, not knowing even what is the size of the M. And now you'll get slightly worse result. This is proof, doesn't mean that you can do anything better. 1 plus little o of 1 times lan M plus order log 1. And the result holds even if the guesser has lots of randomness and all the crypto assumptions in the world, and the dealer is computationally efficient. So what can you do? What can you do? Given that these are the rules of the game, there isn't much the dealer can do. The dealer can put it at the end of the day. I'm not going to use that card. You made a guess. The guesser made a guess. Let's say it's a good guess. It's reasonable. In which case, meaning that it's a card that has a good. In which case, what the dealer would do is put that card at the end of the. It means that the guesser is aware that this card is out there. So I'm not going to use it. So this is the move to the back adversary. As I said, you refrain from drawing a recently guessed card. And the thing is, if you put too many cards at the end of the deck, you're going to run out of cards. So what you do is you reshuffle every once in a while. Okay, so the game starts with drawing at random. You stop at some point. You reshuffle the deck. That's meaningless at this point because you shuffle. And then you play move to the back for a few rounds, and you reshuffle. Move to the back, reshuffle. Move to the back, reshuffle. Towards the end, you give up because the guesser may figure out what is the remaining deck by clever encoding. So you also draw a time. And the only question is really how large these epochs need to be. And so sort of not sophistication, because it ended up not being so sophisticated. But the thing you need to pay attention is the size of these epochs. When are you going to do the reshuffling? Okay, but you don't need to know anything about the algorithm of the guess. And the one when you don't even need to know anything about the size of M is you can play around with the size of these epochs when you do the reshuffling, starting with very large M and going down as things progress, and you get the result. Okay, so really in the adaptive case, crypto doesn't help. Crypto randomness, all these things don't help. There's nothing much you can do for the adaptive. Okay, so let's talk about the history of card guessing. Yeah. So the first paper we found talking about it is by Ronald Fisher, who published it. Look where. So the question was, how do you, Ronald Fisher tried to analyze is somebody claims that they can guess cards. What does it mean that they can guess cards? So he analyzed, in this case, it was a little bit more complex. It was the type of problem where you have CI copies of the I card. And let's say I think he analyzed the case with either full feedback or no feedback. Anyway, so he analyzed it and published it in where you publish such things, of course, in Psychical Research Volume 34. And so a couple of years ago, Diaconis and Graham analyzed it more in our terminology. And more recently, Diaconis, Graham, and Hero, right here, in San Diego, analyzed the card guessing with partial feedback. So in fact, we don't know what to do in this case with partial memory. We don't know what you can do once you have one CI is larger than one. I mean, we analyze the case, so each card is unique. You don't know what to do if it's not unique, because you don't know the open problem. And of course, card counting appears in Blackjack, where Thorpe was the first to write about it. I assume not the first to do it. And he showed that a winning strategy for 21, which essentially suggested low memory strategies that are human computable that increase the player's expected benefits. Because knowing the distribution of the next card helps to evaluate your own hand. And it's relevant in many other games. And here you can see Russell doing it in forming it in Hangover. Okay, so I guess the conclusion is those who cannot remember it are condemned to repeat it, or who cannot remember the past are condemned to repeat it. Famous quote of Santayana. But it's true in this case, even if you use randomness in cryptography. So having said that, let me switch over to the case. Let me skip. That's a good question.
So, you remember how he showed it on the first?
Okay. Okay, maybe let me just mention everything I said so far was talked about the guesser with low memory, but you can ask, what happens if the dealer has low memory? What can we do? So what we can show is that there exists a strategy for an M-bit dealer against the guesser, which is all powerful. And if you think about it, what can you do with M bits? Well, let's say you choose from 1 over M cards each time, then you will get something like N over M. And this, indeed, you can get this bound. Think of it as a sliding window, size M, and you're always selecting from the last M. Well, you'll always be selecting from M cards that haven't appeared so far. And the trick is, how do you encode? I mean, in general, you cannot encode M cards that appeared using M bits. You need M log N, but you can actually do something pretty close to that in expectation. And so with M bits, you can limit the dealer to something like order N over M, the correct guesses. And this is the best possible. You cannot go below that. And the proof is, surprise, surprise, also based on encoding. And but here, crypto one-way functions clearly help, because you can use, if the dealer has a small short seed, the dealer can use it in order to generate, let's say, a pseudo-random generator. From the pseudo-random generator, generate a pseudo-random function. From the pseudo-random function, generate a pseudo-random permutation, and then use the pseudo-random permutation. In the ith round, you are going to output pi of I. And thanks to, you can even generate a permutation. So crypto here helps. Crypto helps, and the question is whether crypto is necessary in order to get the lower value. There are no one-way functions. You cannot break this. In other words, whether in Pestilent and below, whether you can do better, whether you can do better than you cannot do better than NOV. Okay, so let me end up with setting that I'll first convince you that it's very related, and then I'll convince you that they're unrelated. No, they are related. So here is a very fun game suggested by Garg and Schneider of 2 players. Also a game which sounds a little boring, but will become more interesting very soon. So we have two players, Alice and Bob. Alice goes first, Bob goes second. In each round, they pick a value in the range 1 through 2n, and that has not appeared so far. If any player repeats a value that has appeared already, that player loses the game. All the numbers are picked, it's a draw. Again, not a very interesting game if they have perfect. But the question is, what can they do? Is there any strategy? Any low memory strategy for any of the players? Here's the hint. Mirror game. Russell?
So you,
Careful up. Exactly. You give the other guy, because by the very fact that the opponent didn't lose when they saying I, means that the one paired with I has not been, neither I nor the one paired with I has been. That's exactly the strategy I use when I'm standing in front of the fridge and it's open. I can forget that I'm hungry, because I wouldn't be standing in front of the fridge with the door open if I'm not. So it's exactly this principle. Yeah.
The question is, are you hungry enough to eat what's in the fridge? It's not whether you're hungry, it's whether you're hungry enough to eat
What's in the fridge. Yeah. Okay. And I think I used the same analogy once about 10 years ago. And was it Manuel or Abrin? Told the story about von Neumann going, not remembering, talking in the middle of the campus, asking someone, where did they come from, here or from there? He said, from here. Ah, that means I've eaten already. Okay, so with perfect memory, they reach a draw. The second player has a strategy that requires very little memory. And what Gorgen Schneider showed is that Alice does not have a deterministic strategy that uses sublinear space. And guarantees a draw against any strategy of Bob's. So that's very curious, because you could think that maybe Alice can imitate this strategy. But of course, she doesn't have a perfect matching. So, well, what can you do? So how are you going to use it? And they found a very nice way of expressing it. And what what they did show is that if Alice has access to secret matching, then you do have a strategy that does something, requiring something like square root of n bits of memory, but it requires Alice having access, and this is related to what Tony was asking, assuming Alice has access to secret match. And they needed all sorts of technical things, but it's really the issue is the secret matching. And Orifage showed that you can use it using log cube bits. And if you think about it, what we just saw, it allows you to get exactly this, to reconstruct these results. You can replace the matching with a cryptographic one. Let's say you can also get a matching there's work that Omer Rangold and I did, how to get a pseudo-random involution from pseudo-random permutation. So you can get, using a short key, you can get a secret matching. And now you can answer based on the secret matching, but each time remember which card you picked a random card. And you can use, you don't need to remember anything, except that from time to time you have to follow which card have appeared so far and which haven't. And at any time, at any time, there is the guy who is unmatched. And if the other guy, if this one is picked, you need to pick another one that hasn't appeared so far. But how many times will the adversary, in this case, the second player, pick the unmatched guy? Remember, the unmatched guy is random. It's going to happen in expectation log n time. That means that you can use the methods we just saw, but you need just log n times to have a good guess. So you get these. So anyway, so in this setting, for instance, if you have a secret, if you have, let's say, a pseudo-random matching, and you have the stuff that I discussed before, then you can get a good strategy. So, of course, here we need two things: that Bob cannot break a one-way function, that we have a one-way function, Bob cannot break it. And we need the assumption that you can, that Alice has secret memory, that Bob cannot see what she's remembering. You can ask what happens in the open book, full information model. So everything is known except future coin flip. Okay? And let's say also give us unlimited randomness. But Alice can see the unlimited, and Bob can see the unlimited randomness. Anything that Alice has access to, Bob has access. These are the rules of it. So here, what Roy McGinn and I showed is that if Alice has no secrets and memory of size at most, let's say n over 4c bits, then there exists a Bob that against him Alice loses with a probability which is exponential in C, with 1 minus exponential in C. It requires the open book case. And the idea is to play along with at random until a certain turn, and then looking at Bob's memory, find two sets S1 and S2, such that the real set that has been used is one of them. Their union is even, and the probabilities, the conditional probability given Bob's memory, are roughly the same. Once you have this, once you have such a thing, you from this turn on, Bob chooses a number that has not been used so far and is not in S1 union S2. And from parity reasons, Alice is going to be the first one to choose from S1 union S2. And with probability at least half, she's going to choose the wrong one. Chooses the wrong one, then of course she loses. Okay? So this is the strategy. This is, you can use it and you can do it and amplify it and use it several times. And this is the fact that you have such a composition follows from Berlecamp's odd term that says that in any collection of subsets where every set is of even cardinality, which is what happens in our case, and the intersection of every two distinct subsets is odd, there can be at most a capital N such a subset. So let me, there have been a lot of work, a very interesting work on adversarial, in general, adversarial streaming, adversarial sampling, and also stuff I mentioned, the white box case where you actually, the adversary sees what's inside the memory. Also, another interesting paper is by Stockel from Soda. Also has the dichotomy between static and adaptive adversary when you always have to announce a missing item. You see a bunch of items being streamed and you always have to announce the missing an item that is value that has not appeared so far. And I think that goes to your talk from previous workshop at the medical. So open problems. as I mentioned, do we really need, is this the exact expression, or can we get to 1 minus little over 1 times lambda n with only log squared bits? The problem of when you have several types, like what happens if you have a regular deck, but you don't see the suit, but you only see the value. You don't know whether it's ace of club or ace of spade. You just know that it's an ace. And what I mentioned, the problem that I mentioned regarding memory limited, and the exact relationship between, can you use any of these ideas to help you in so many, anyway, happy birthday, Russell. And this is Russell, maybe about 10 years younger than the start of the talk. This is with my daughter, Yael. And I think, everyone wants to claim that they're like Russell, but I think that I have a proof here. And I think that she's not sure whether it's me or not. In this case. Thank you.
Thank you very much, Moni, for a wonderful talk.